That's that's hot. Okay. So, welcome back everyone to my live stream. I know no one is watching, but it's okay because I know you guys are probably going to watch. So, it's good to be back. It's pretty good to be back. Well, what happened? The live stream just restarted or what? Hold on, if I go to YouTube again. Whoops. Actually put back. What if I just Oh hey, what's up? Here, what if I share my screen? Yeah, let's share the screen. Oh, what's up? A Team Dream Action. Oh hey, what's up, David Ninja King? Yeah, what's up? How are you doing? I'm doing great. I'm doing great. Thank you. I just said that. What are you talking about, bro? Dude, why are you copying me, man? What is this? Dude, stop. What are you doing? Bro, dude, what in the world is this? What are we playing right now? Dude, shut up. What are you doing, man? You know what? That's it. I quit, bro. All right. I mean, my gosh, that's so not cool. Whatever. Well, it's good to have you all here today because we're gonna be doing some more calculus. Some more calculus. We're doing L'Hopital's rule in indeterminate forms because why not? So I am going to no, I don't see my email, guys. Cool. Does it matter? Perfect. So we're going to do our homework. I just watched all the lectures, took quite some time, but I believe it was pretty productive. And it's actually very interesting. Um, Here, let me take out my diagram. Let's give a pretty good summary. So, indeterminate forms. Here's what we have. So, we can have an indeterminate form as a quotient, which is where we have infinity over infinity or 0 over 0. And okay, you know what? I'm not gonna explain this. It's fine. I don't think you guys care. Um, so you're making slides for your German class. Okay, cool. Yeah, good luck with that. We got 16 problems. Well, since we don't have a lot of people in here, I am just going to do this on paper, and then we will use our sketchboard. Let's see. So we have to evaluate the limit using L'Hopital's rule of necessary. So we have the limit as x tends to 0 of e to the power of x minus 1 over sine of 13x. Interesting. So let's see if we must use L'Hopital's rule. Well, what we can do, what we can't do, no, what we have to do. So as x approaches 0, we have e to the power of x, and that tends to 1. 1 minus 1 is 0. Okay, so the numerator is 0. And in the denominator, we have sine of 13x. So as x tends to 0, we will have sine of 0. So sine of 0 is 0. So we have 0 over 0. And what does that mean? So that means we must apply L'Hopital's rule. So therefore, we have the limit as x tends to 0 of, so the derivative of e to the power of x minus 1 is simply going to be e to the power of x times the natural logarithm of e, and that's simply, e raised to what power is e? That's 1. So e to the power of x times 1, that's simply e to the power of x. Perfect. So we have e to the power of x over, and the derivative of sine of 13x is going to be cosine of 13x times 13. Beautiful. So if that's the case, which it is the case, as x tends to 0, e to the power of 0, that's going to be 1. And cosine of 13x times 13, well, 13x, that's cosine of 0. Cosine of 0. What is cosine of 0? Wait, what? Sorry, I thought stupid. I think we have 1, right? 1. 1 times 13 is 13. So we have 1 over 13, I believe. Might have gotten something wrong over here. Beautiful. Okay. What did this video do? Yeah, they just did it here. Let me just see a video real quickly. Yes, ma'am. Yes. Sounds good. Yes, ma'am. Yes. Preach it, sister. Ukraine. Whoa. Are we getting political here? What? Infinity or why did she put infinity over infinity? Oh, wow. I completely forgot about that. That's right. Yes. We're not applying the derivative of the entire fraction. We're only applying the derivative of the individual terms in the numerator and the denominator. If we were doing the entire fraction, then I believe I mean, yes, we would have to apply the quotient rule, and that would be a little more messy. It's totally manageable because we cooked last week, but but no, we don't have to do this right now. You know, if we would, we would have gotten like a e to the power of x times sine of 14x minus e to the power of x minus 1 times cosine of 14x times 14, I think, over sine squared of 14x. Let's change. There's a 14. Okay. Yes. Mm-hmm. Right. Right. Uh-huh. Yes. No, thank you for your help. Awesome. Yes. So I think we're understanding everything that has to be done over here. Screen is not big enough. Is what if we like do that? Okay. Well, let's continue because that's one app. Why? What's this, bro? Guitar tutorials. All right. Let's continue. So, evaluate the limit using L'Hopital's rule. We have the limit as x tends to 0 of sine of 2x over tangent of 3x. Gotcha. So plugging in 0, we get sine of 0, which is 0, over tangent of 0. So 0 over cosine of 0, which is what's cosine of 0? 1. So 0 over 1 is 0. So we have 0 over 0. So that's an indeterminate quotient. And if that's the case, which it is, so we'll have to apply L'Hopital's rule. So we have the limit whoops, the limit as x tends to 0 of cosine of 2. Okay, fine. We got it here. 2 times cosine of 2x over 3. Oh, wait, and the derivative of tangent was secant squared, I think. 3 secant squared of 3x. Beautiful. So, plugging in 0, we get 2 times 1, which is 2. Cosine of 0 is 1. 2 times 1 is 2. 2 over 3 times. Okay, and what is secant? Do I have to know what secant is? Wait, hold on. First of all, derivative of tangent, that's secant squared, right? So if that's the case, then secant squared of 3x, not integral, but huh. Wait, but okay. First of all, what is secant? Whoops. What is secant? So secant is um okay, first of all, what is secant of 3x? What is secant of 3x? One over cosine. Okay. 1 over cosine. That's it. 1 over cosine. So if that's the case, which it is, like why do I keep saying that? So we have um we have 2. Let's put this 2 in the middle. So we get 2 over over what? So we have 1 over cosine squared of 3x. And if that's the case, okay, so cosine of, oh, well, I mean, dude, my bad. So this is cosine a square root of 0. So cosine of 0 is 1. 1 squared is 1. 1 over 1 is 1. 3 times 1 is 3. So I believe we get something like 2/3. And that's correct. Let's go. Let's go. Cool. Let's continue. So we have the limit as x tends to positive infinity, or yeah, just positive infinity, of 10 times the natural logarithm of x over x. So for infinity, the natural logarithm of infinity, e to the power of what gives infinity? That's going to be infinity. 10 times infinity is infinity, so we have infinity over infinity. So we have to apply L'Hopital's rule. The limit as x tends to positive infinity, and then we apply the derivative So we get 10 that stays there. And the derivative of a natural log is going to be times O1 over x. And this is all over the derivative of x, which is simply 1. So we have 10 times 1 over x, or 10 over x. So 10 over x, that's going to be 10 over infinity. And that's simply 0. We're cooking. Right. Uh-huh. Yes. Let's continue. Yeah, I wonder why not a lot of people are joining the stream. I think the last stream I did a few days ago, it got removed by YouTube because I violated some like terms or policies of YouTube or something. I mean, I don't know what he did, and they didn't leave an explanation why. So, and I think somewhere I remember I read that they will like my live stream would not appear in many people across YouTube, but it's okay. Yeah, yeah. I see you. Thank you. I thank you for being here. I appreciate you. All right. So let's continue. So we have the limit as x tends to 0 of 14 to the power of x minus 12 to the power of x over x. So 0. So we have 1 minus 1 over 1. 0 over 1. Oh, so do we? So is that simply 0? Oh, no, no, no. We have a 0 over 0. Forgive me. So, applying L'Hopital's rule, the limit as x tends to 0. So then, since we have exponential functions, so what we do is, so we have 14 to the power of x times the natural logarithm of 14, I believe, minus 12 to the power of x times the natural, whoops, nope, times the natural logarithm of 12 over x, 1. I see. And then, cool. So applying with 0, we get 1 times, so I believe we have now the natural logarithm of 14 minus the natural logarithm of 12. So what do we do in that case? So, I mean, I think that's the most we can simplify. Okay, what did we do? I feel like I'm just applying an equation. So yeah, so we had an indeterminate form, an indeterminate quotient, 0 over 0. So we simply applied L'Hopital's rule, and we found out that this value is the rate of change. Okay, cool. Now we have the limit as x tends to infinity of 8x squared minus e to the power of 6x. Cool. So to the power of infinity. Infinity over infinity. Yes, that was fake. All right. So 16x over e to the power of 6x times 6. 6e to the power of 6x. Then, oops, let's limit. So now what? Yeah, now we try to see if that's it. Is this simple? I feel like so we have infinity over infinity. That's still an indeterminate form. So we have to apply L'Hopital rules again. We have to do it again. And then here we get 16 over uh let's do this. So we have 36 e to the power of 6x. And if that's the case, which it is, we have 0. We haven't gotten a single question wrong. This is getting frightening. I'll probably yeah, cool. Yeah, I don't think we need a video now. We're like understanding. We could be teaching this class, you know? Let me teach the class, professor. I think I'm getting this well. Trust. Um there's nobody here or almost a nobody here. Well, thanks Nicola for staying here. Hello. Hi. But Blake, I can't hear you. I can't hear the third person. I swear this guy's so annoying. He keeps copying me. Gotcha. Well, we have more homework to do. So we have to evaluate the limit using L'Hopital's rule. So we have the limit x tends to 0 limit of x to the power of 3 over sine of x minus n. What are you doing? So now we have x tends to 0. I see. Shut up. Hold on. So let's see if we have to use L'Hopital's rule. So we have 0 over sine of 0, which is 0 minus 0. So we have 0 over 0. That's an infinite quotient. And if that's the case, which it is, now we have to apply L'Hopital's rule. So we have the limit of x tends to 0 of 3x squared over cosine of x minus 1. And if that's the case, which it is, now let's see if we get to where we need to go. So we have 0 over cosine of 0, which is 1. 1 minus 1 is 0. So no, we have still 0 over 0 and indeterminate quotient. So we have to apply L'Hopital's rule again. So we have the limit as x tends to 0 of 6x over negative sine of x. And then if that's the case, which it is, we have 0 over, and sine of 0 is what? Sine of 0 is what? Sine of 0. That's sine of 0 is 0. So we still have 0 over 0. So we have to apply L'Hopital rule again. So the limit as x tends to 0 of 6 over negative cosine of x. And that's going to be 6 over, wait, hold on. In the cosine of 0, what is cosine of 0? Cosine of 0 is 1. So we have 6, we have negative 6, and we press submit, and we get it right. Let's go. We're getting everything correct here. Let's go. Yes. Let's go. Yes. Let's go, bro. Yeah, okay. How fast can we complete the next one? We still have like 10 questions left. So let's see. So here we have the limit as x tends to. Wait, why can't I hear the other guys? Yeah. Oh, why can't I hear you, bro? Hold on. Over here, live chat. No, it's not that. Why don't I have access to this feature? I don't have access. Pop out dashboard, channel level settings. Uh, yeah, it's not that. I mean, I want to share. Can it edit it? Oh, wait, no. That's not it, right? Uh, message. Redirect trailer. No, it's not that. Live chat. Cool. All right. Let's keep going because why not? So we have the limit as x tends to 0 of 3x plus tangent of 4x. This is going to be over 2x minus tangent of 3x. We have tangent. Let's see. So let's see if we should apply L'Hopital's rule. So 0. So we have 0 plus tangent of 0. Tangent of 0 is going to be 0. So 0 over 0, we have an indeterminate quotient. We have to apply L'Hopital's rule. So we have the limit as x tends to 0 of, let's see, so the derivative 3 plus, and the derivative of tangent of 4x is going to be secant squared of 4x times 4 per the chain rule. This is all over 2 minus secant squared of 3x times 3. Yeah, simplifying this a little bit more, we have the limit as x to 0 of 3 plus 4 secant squared 4x over 2 minus 3 uh, secant squared of 3x. Beautiful. So what if we now replace 0? So we have 1. Can't square. Okay. So it looks like we're gonna have to do all of this again. Awesome. So 3, 4 times 1 over cosine squared of x. Um, let's see. And then this is gonna be over 2 minus 3 times 1 over cosine squared of 3x. That's insane. So if that's the case, which it is, this is what happens. 0. So cosine of 0, 1. Oh, what do you look at that? So we have 3 plus 4 over. Wait, hold on. And cosine of 0 is 1. Cosine of 0 is 1. Cosine squared of 0 is therefore, oh wait, yeah, 1 as well. 1. So then we have 4 over 1. So this is literally plus 4 over uh, 2 minus 3. So this equals 7 over negative 1. This equals negative 7. We negative 7. Wait. Negative. What is so? I'm confused. Enter negative infinity if your answer is negative. Okay. Oh, I see. But we got negative 7. Dude, up to this point, I literally was like almost guessing. The arithmetic, I wasn't even paying attention. But looks like we are getting our arithmetic right. Um or our algebra right. Okay. And I think we're getting this uh pretty well. Who am I talking to? Well, my friend, you see math. Even if there's nobody around, you talk to yourself. I was kidding. Yeah. I'm talking to myself, Nicola. Or just for fun. It helps me a process of the information. I'm sorry if it's annoying, but we shall continue because we still have 389. We have 9 problems left. We're doing well, but let's see if we can go through the entire homework without getting something wrong. So, complete the following. Gotcha. I see. I see. Okay. So we have the limit as x tends to 1 of 7 to the power of x minus 7 over x squared minus 1. All right. I guess let's try to understand this a little more intuitively. So, this equals to, as x tends to 1. So 7 to the power of x, 7 to the power of 1, 7 minus 7 is 0. X to the, 1 squared is 1, 1 minus 1 is 0, 0 over 0, that's an indeterminate quotient. So, applying L'Hopital's rule, we have, and here we have an exponential function. So, 7 to the power of x, 7 to the power of x times the natural logarithms of 7. Perfect. This is over 2x, 2x, literally that. So with 1, we have 7 times natural logarithm of 7 over 2. I think that's pretty good, right? 7 times the natural logarithm of 7 over 2. And then we have to solve for, whoa, interesting. Tangent inverse of x over 1 over x minus 7. I see. Okay. Oh, wait, hold on. Oh, wait, no. Let's erase this because this is a limit as x tends to infinity. The limit as x tends to infinity of tangent inverse of x over 1 over x minus 7. Cool. We brought back inverses. So let's see. Infinity. Tangent inverse of infinity. So the inverse of tangent. Wait, hold on. So what are we doing? Yeah, we just want to see if we get an indeterminate quotient or not. Wait, here, I want to. Okay, no. Let's do this ourselves, and then let's see how the video does it. So, in the bottom, we have 1 over x. 1 over 0 is. I'm sorry, we have tends to infinity. So, 1 over infinity, that is 0. So we have negative 7 in the bottom. And tangent inverse of infinity. So we have sine of infinity. What is sine of infinity? Is that does not exist? Here, let me see the video.
Now, as
Yes, what we got. Wait, what? Why? Oh, whoa! Don't tell me we forgot that. Oh boy. Was it this one? Oh, where we saw. Oh boy. Uh, yeah, so here we have our restricted domain because these are, oh yes, so we know that the domain of tangent inverse of x is going to be from negative pi over 2 to pi over 2 exclusive. And the, oh yeah, so yeah, the domain of that is going to be negative pi over 2 to pi over 2 exclusive. And then the range of arctangent, well, it's going to be the domain of tangent. And the domain of tangent, I believe it's going to be um all odd multiples, I think. Oh, excuse me? Wait, what? I'm confused. Hold on. Oh, wait. Oh, sorry. The restricted domain of tangent is negative pi over 2 to pi over 2. Oh, so that means the range of tangent is going to be negative pi over 2 to pi over 2. And the domain of tangent is the range of tangent of x, which is negative infinity to infinity. Uh-huh. Oh. Okay. Uh yeah, I remember that. Okay. And yeah, we derivatives of inverse functions I think is important. Yes. Huh? Yeah, no. I think I remember that. Okay, I think we got that. Perfect. So, where are we? So we have as x tends to infinity. So our domain of tangent inverse of x is going to be our domain, our domain. Our domain is going to be, so it's going to be the range of tangent of x, and the range of tangent of x is negative infinity to infinity. So that's our domain. Perfect. And then in our range of tangent of x, sorry, our range of tangent inverse of x is the domain of tangent of x, which is negative pi over 2 to pi over 2. So this is, I believe it's going to be uh to go to the bathroom. Pi over 2 over negative 7, I think. Got that right. Okay, I'll be right back. All right. There you go. Perfect. Let's go. So, and how do you do it? Mm-hmm. Right. Mm-hmm. Mm-hmm. Right. Um. Yes, that's right. If we had an indeterminate form, you would have to apply L'Hopital's rule again, but we don't. So that's good. Yes, I remember you. I remember you. Yes. Were you from last live stream or the one before? Oh, well, either of them. Either of them. I think I remember you. Yeah, yeah. Thank you. I thank you for coming back here again. Here, I guess it's time to now. Um, it's time to do the problems in the whiteboard. Cool. So, yeah, well, it's good to have you back again. Let's see, where are we? Yeah. What did I just close? Okay, it's fine. We don't need that right now, and we don't need that. So, question 9: evaluate the limit using L'Hopital's rule. Uh, the limit as x tends to pi over 2. That looks like a z. Oh, there we go. Of 8 cosine of negative 5x times secant of 3x. Cool. So, let's see. So, directly replacing pi over 2. So, cosine of negative 5 times pi over 2. So, pi over 2 is. Okay, hold on. So, I think what we'd get 8. Whoops. 8 times cosine of negative 5 pi over 2 times secant of 3 pi over 2. Now, will that give an indeterminate? Oh, okay. Hold on. Yes. Let's see. So let's try to get this into a. Since this is a product, I guess let's reciprocate one of our terms. So I think we get 8 here. What if we just reciprocate cosine. Oh, no. Let's reciprocate secant. Is the reciprocal of secant 1 over cosine, or is that literally what it equals to? Wait, hold on. Wait. Reciprocal of secant is cosine. Oh, for real? Oh yeah, because secant equals to 1 over cosine. So yes, makes complete sense. Oh, awesome, dude. So wait, but so we want a quotient though, and the reciprocal of cosine is secant. Reciprocal of cosine, and this is secant. Yes, inverses, whatever. So it's fine. Let's just do secant and let's see where we get. So 5 pi over 2. Five pi over 2. And then we have all right, let's do 1 over secant. Over 1 over secant of 3 pi over 2. And if that's the case, so now, hold on, let's pull up the unit circle. Yes, let's pull up that unit circle. Where are we? So, here, I'm just gonna move it over here. So, negative 5 pi over 2. Where do we find that thing? Negative 5 pi over 2. Yeah, no, we're not going to find that there. Oh, wait, I'm sorry. I'm so stupid. I found 5 pi over 6. Hold on. So, we have pi over 2, 3 pi over 2. Or here we have pi over 2, 3 pi over 2, 5 pi over 2. So cosine of negative 5 pi over 2, that's going to be negative 1. So we have negative 8. And then secant of 3 pi over 2. What's 3 pi over 2? Where's 3 pi over 2? 3 pi, sorry, we have 2 pi over 3, but we want 3 pi over 2. So where's pi over 2? 3 pi over 2. Secant. What is secant? 1 over secant literally equals. Wait, 1 over secant? No, wait, what? That's the same thing as 1 over. Wait. Reciprocal of secant. Is cosine. All right, so secant equals to 1 over cosine. Secant equals to 1 over, yeah, right, that makes sense. Secant is the reciprocal of cosine. So if secant equals to 1 over cosine, then we have 1 over cosine of 3 pi over 2. So we have 1 over cosine of 3 pi over 2. Beautiful. So if that's the case, cosine of 3 pi over 2, that's going to be negative 1. 1 over negative 1. That is, so 1 over negative, so this 1 over negative 1. No, not 7, 1. And this is simply equal to negative 1. So this is negative 1. Or in other words, this is 8 over 1. Or in other words, that's equal to 8. 8, right? All right. We finally got an answer wrong. Okay. Well, I mean, I think, let's see. What do we get wrong? I mean, I think we had like the correct approach, but we eventually got something wrong over here. So, Let's see. So what do we have? We have the limit as x tends to pi over 2 of 8 cosine of negative 5x times secant of 3x. So, so checking if the function has an indeterminate form, we have 8 cosine of negative 5 pi over 2 times secant of 3 pi over 2. Beautiful. So let's go back to the unit circle. Oh, whoops. Now, simplifying further, we have 8 cosine of negative 5 pi over 2 over 1 over secant 3 pi over 2. Yes, that's right. So cosine of negative 5 over 2, a negative 5 pi over 2. So we have negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. That's hot. Awesome. So negative 5 pi over 2. Cosine of negative 5 pi over 2 is negative 1. Negative 1 times 8 is negative 8. So in the numerator, we have negative 8. And then in the denominator, we have 1 over secant of 3 pi over 2. Secant of 3 pi over 2 is the same thing as 1 over cosine of 3 pi over 2. Yes. So cosine of 3 pi over 2 is negative 1. 1 over negative 1 is negative 1. And then we have 1 over negative 1 is negative 1. Negative 8 over negative 1, well, that's 8 over 1. And 8 over 1 is 8. What did we get wrong? Oh. Yeah, I mean, this should work because we did not go to an indeterminate function. Oh boy. I mean, I don't want to ask ChatGPT what he got wrong, but I don't want to waste all the time because we still have 1, 2, 3, 4. Wow, we still have 7 questions left. We have a lot. So what's going on here? Wait, but I'm confused. It says evaluate the limit using L'Hopital's rule, as if we need to use L'Hopital's rule. Wait, so we don't check if the limit gets to an indeterminate quotient or something? Oh, no. That should work. So do we like immediately use L'Hopital's rule? Wait, why is the limit an indeterminate form of type 0 times pi? Wait, why? Wait, no, but why? I mean, that makes utterly no sense. Yeah, here. I think I'm going to ask a Copilot. Because this is not making sense. Does this limit get to an indeterminate form? Yeah, it's not needed here. 5x, 5 pi over 2. Wait, what? Cosine is... no! No way we actually got that wrong. This is not negative 1. This is 0. This is 0. Oh, that's why. So, 0. So I'm just going to erase that. 0. And then, so in fact, I'm just going to erase all of this because this is wrong. So this is equal to 1 over 0. 1 over 0. This is equal to, in 1 over 0, what is that? That's like infinity. And 1 over infinity is 0. So so we do have an indeterminate form. My mistake. My mistake, everyone. That was not cool. But it's good overall because it's it's a it's a learning experience, you know? So we have 0 over 0. So we have to apply L'Hopital's rule in this function. I see. I see. Okay. Cool. So what do we do? The derivative of all of that. Wait, hold on. No, 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 no. I mean, we did arrive to a quotient. So we do L'Hopital's rule on the quotient, I think. So we have 8 or negative 8 sine of negative 5 pi over 2 times hold on, wait, what? Where's x? Oh, wait, we have pi over 2. So oh wow, this is actually kind of tough. Wait, no. Oh, okay, hold on. Dude, my back is suffering. Yeah, this is important. Hold on. What do we apply L'Hopital's rule to? We apply it to the quotient. Let's see, dude. What do we apply L'Hopital's rule to? Hold on, I'm just gonna open up the lecture again because I think this is really important. Oh, and this is the product part. So yeah, so you put this in the form of a quotient, and then you take L'Hopital's rule. So we're not replacing anything. Yes, you do it. I see. Cool. Another learning experience. This is good. So you don't do it here. You don't do it here. You do it in negative 5x. Sorry. Times negative 5. I think negative 5, negative 5. Yeah, a derivative. Over 1 over 3 secant of 3x. That's what we have. Sorry, no, that's the derivative. Well, actually, not quite. The derivative of secant is secant of 3x. Ooh. Tangent of 3x. Hold on. Think, dude. Think. So 1 over 3 secant of 3x, tangent of 3x. Is that right? Hold on. The derivative of secant of 3x is 3, the derivative of g prime of x, times, and then the derivative of the outer function, evaluated at the inner function. So that's secant of 3x times tangent of 3x. Okay, I think we got that right. So now, checking if this is an indeterminate function. Okay, and sorry. In fact, let's simply simplify this. 40 sine of negative 5x over 3 secant of 3x tangent of 3x. Cool. So that's what we have. It looks very organized, very cool, very hot. Oh, I gotta go. All right. I'll see you, Nicola. So now we check if we should apply L'Hopital's rule by plugging in pi over 2. So 40 sine of negative 5 pi over 2. Let's see. Negative 5. Oh yeah. So let's go back to the unit circle. So we have negative 5 pi over 2. So negative pi over 2 Negative 3 pi over 2, negative 5 pi over 2. Negative 5 pi over 2 right here. Negative 5 pi over 2 right here. Hold on. Why did he say pi over 2? I'm actually getting a little concerned. Mm, 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 mm. Oh, no. I'm sorry. My bad. No. My bad. So we have 3. There you go. Huh. So sine of that. But we have a negative 5. No. Good. Negative 1. So this is equal to negative 40 over, and then 3 times secant of secant of 3x. Oh boy. Secant of 3x is 1 over cosine of 3x. So we have 3 times 1 over. Yeah, am I using this the way I'm supposed to? 1 over, and cosine of 3x, or 3 pi over 2. 3 pi over 2. Pi over 2, 3 pi over 2. Cosine of that. Cosine of 3 pi over 2 is 0. 1 over 0. 1 over 0. Hold on. Wait, what? You have got to be kidding me. It's over 1. Come on, dude. Don't do that. 1 over 3 times 1 over 0 plus, and tangent of 3 pi over 2 is sine of 3 pi over 2. So we have negative 1 over cosine of 3 pi over 2, which is 0. And further simplification gives us negative 40 over 1 over, 1 over 0 is infinity. Infinity plus, negative 1 over 0. That's negative infinity, right? So minus infinity. Well, I'm getting stuck. Oh boy. Oh, I'm kind of getting stuck, guys. Oh. Huh. I'm getting a little tired. We go 1 hour and 5 minutes. Okay. Well, let's continue. So let's go back to the unit circle. Oh wow, dude. So three. So we have 1 over cosine of 3 pi over 2. And there's 0. 1 over 0 plus sine of 3 pi over 2 negative 1 over cosine of 3 pi over 2, which is 0. 1 over 0 is infinity plus negative 1 over 0. Um, Hold on. All right, whatever. Yeah, I mean, I think we're complicating this too much. Well, let's do this again. So we have so secant is when, yeah, literally. Why did we not think of that? So much more simple than what we thought. So let's see. Pi over 2. Negative 5 pi over 2. Please. Oh, let's think about this. We will get 0. 0 over 3 pi over 2. 3 pi over 2. That's 0. Perfect. So applying L'Hopital's rule. We did this right? Yeah. I hope so. I hope so. Oh. Ooh. Yes, right? I think so. So, now, do we get an indeterminate form? So we have negative 5 pi over. Okay, so we have sine. We have, we get negative 40 over, my gosh. That is so ugly. There we go. That's a little better. No, and in fact, it's pretty good. It's understandable. Whatever. So then we have, so 3 pi over 2. Sine of that is negative 1. So we get 3. Well, I believe, ladies and gentlemen, that is our answer. Nobody's watching. That's why did I have to close? Oh, crap. Why did I have to close that, dude? Now we got to go back to our calculus for engineering. Infinity and beyond. What are we saying? We're not saying anything, are we? Let's continue. Only 50% of the way there. That's insane. Negative 40 over 3. Let's go. Let's go. All of that for a stupid problem. Yeah, well, we got to continue, but nobody's watching. I have to win the live stream? No, not yet. Not yet. No, but we can't end right now. We can't. We need to finish our homework, though, because we are in problem 10 and we still have 7 questions to complete. This is not cool. What does that mean? Like, oh, cool. Thanks, dude. Hold on, I have one question. Or in fact, it's more like it's like curiosity. We're doing live. If we go here, is that how I look? I see. Okay. My hair look like that, bro. So funny. Oh, and now there's one person watching now. Welcome. Welcome to the live stream. We're almost done with our homework. Still got 7 questions left. But we got this. We completely got this. Because we have to compute the following limit using L'Hopital's rule if appropriate. So we have the limit as x tends to 0 from the right. It's ugly. There we go. Of 7 sine of x times the natural logarithm of x. There we go. That's much better. Dude, I've been sitting in this chair for so long. Okay, so let's see. Let's see if we get an indeterminate form or not. 7 times sine of 0, which is 0, so that's 0. And then regardless of what the natural logarithm of x is, which is 0, or that's, I think, like 1, e to the power of what is 0. That's what? Wait. No. This is important. Wait, e to the power of what is 0? That's going to be, so e to the power of what is 0? Well, that is e to the power of negative infinity, because 1 over e to the power of infinity of 0 is 0. Perfect. Okay, so we have, I think, like 0 times negative infinity. And that's very conflicting, because then we have an indeterminate form, and therefore we have to apply L'Hopital's rule. From the right. Beautiful. So 7 stays there. Cosine of x times 1 over x. Beautiful. That's so hot. So let's continue simplifying. Wow, dude, why does that look like a goldfish? Or like a fish? In fact, it just looks like a fish. Now, do we get an indeterminate form? 7 times, so cosine of 0 is 1. So we get 7 over 0. This is equal to infinity. This equals to infinity. We got that wrong. What are you talking about? What? So cosine of 0 is 1. 7 times 1 is 1. And 1 over x, or 1 over 0. 1 over 0. What is that? That is infinity. Infinity. 7. So infinity. Yeah. That equals infinity. What did we get wrong? Yeah, that's what we got. Ah, that's right. No, well, come on, no, no, no. We can't get that wrong. I mean, we have, okay, hold on. So, um, I don't. We need to get this in a quotient first. Oh no, sorry. We got to do that after. I see. Yes. So, if that's the case, all right. Here. So we have the limit as x tends to 0 from the right of 7 sine of x times the natural logarithm of x. So, um, oh, I see. Okay. So you did that. But so you're just simplifying then, right? Cosecant. Mm, 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 mm. Oh, whatever. Okay. So let's simplify. So we get okay. Um. Oh boy, I'm getting tired. But we gotta persist. We got this. Okay. Cosecant inverse of sine of x. Now let's see if we get an indeterminate function. No, well, I mean, we simply rewrote this. Rewrote this. Whatever. Um, we why why did we why did we reread it? We gotta put in a quotient. Oh, gotcha. Oh, I see. So what we have over here is an indeterminate product, but not in an indeterminate form. So here we got to put it in an indeterminate form, and then we can apply L'Hopital's rule. I think that's what we got wrong then. So the limit as x tends to 0 from the right, we get 7 1 over x. Fine. 7 over x over, and the derivative of cosecant, or inverse of sine. That's going to be 1 over square root of 1 minus x squared. So simplifying this, oh, dude, I need to go poop. We get 7 over x times 1 minus x squared over 1. This equals to 7 square root of 1 minus x squared. Wait, is that for real? Yeah, a derivative of an inverse function. X. Uh-huh. So now, to 0 from the right. So, is this equal to infinity then? Hold on. So we get 0 at the bottom. Sorry. So 7, my bad. 1 minus 0. That is 1. So square root of 1 is 1. 7 times 1 is 7. 7 over 0. That is infinity. What's up? Oh boy. What? How do you get that? The derivative of cosecant. Oh, wait, no. Nope, that's not it. Wait, cosecant? That's not arc sine, right? Hold on. Arc sine. Sine inverse. That's not 1 over sine, right? No. Yeah, this is wrong. Okay, I see. So let's just follow his guide. So we get the limit as x tends to 7, whoa, to 0 from the right is 7 over x of 7 over x over. So apparently it is. Wait, hold on. So derivative of cosecant of x is negative cosecant times cotangent. Ooh, bro. Cosecant of x times cotangent of x. Okay. Um. So cleaning this up, he also do this, right? What? Oh, oh, I see. I see. Okay, there you go. Excuse me? Over X. Uh-huh. Yep. I'll provide that. So now, what do you do? Limit. Okay. So that was the derivative. Uh-huh. Yeah, I simplified. I'm feeling we're gonna have to apply the rule again. Why did you get -4? Oh, that's right, because I have a negative sign. Uh-huh. Mm-hmm. Oh, I see. Okay. So now we can simplify. Sine of x. Wow, dude. Hold on. Sine of 0. Oh, what is that? Sine of 0, bro. It's not that hard. The y. So that's 0. We have, yeah, 0. But hold on. So, and cosine of 0 is what? Cosine of 0 is 1. 0 over 1 is 0. So here we have 0 over 0. So do we get 0 or? Oh, wait, hold on. And uh, sine of x. Sine of 0 is what? 0. 0 over 0. Why is that 1? What are you doing? Wait, why? Um, Side of x over x. No, dude. Okay. Yeah, well, regardless, it's still going to be 0. Okay. Gosh. All right. We still got, what, 6 problems left. Oh, boy. All right. This shouldn't be very hard. Come on. Come on. We got this. Oh, dude. I'm tired. I'm tired, guys. But let's finish this. Okay, so 2e. Bro, All right, 0. I think. I think that's your answer. Yeah. Oh, okay. What's up? This is a Calc 1. They tried using hospitals. Lopitals. Yes, yes. That is what I'm doing. Oh no, I forgot. Got to put it in a quotient form. Oh, okay. Let's do this again. Dude, I'm getting tired of this topic because I feel like I'm repeating things, but yet I'm, I'm just gonna stop talking. I don't know what I'm saying right now. Okay, so get. That's what we get. Okay. Wait, 1 over infinity is 0. Yeah. So we have infinity minus infinity. So now let's use L'Hopital's. So we get hold on. So if this, okay? Mm. Oh wait, hold on. We don't have a product though. Okay, wait. So what do we do? Oh, dude, wow. This is tough. Right. Yeah. Mm-hmm. I see. Okay. Wait. Oh, I see. Okay. Yeah, I guess we could do that. So let's try doing that. So factoring 2x, we get Mm-hmm. All right, cool. Okay. I think we, I think we got it from here. Uh, let's see. Dude, no, what happened now? Hold on. So, yes. Uh-huh. Yes. That's a good idea. Okay. Oh, okay. We're back. We're back. So here's what we're gonna do. So now we got two products, and now, we got to put this in a quotient now. In fact, no, no, no. Let's do perfect. Now in this case, let's see. So to infinity, we have 1 minus 1. That's 0. Then we have 1 over infinity. So we have 0 over 0. So we still have an indeterminate function. So we take the derivative of both sides, and that's going to equal to times, oops, over, and the derivative of 1 over a 2x is going to be, so we have 1 over 2x prime, bro, that is 1 times, uh, dude, what is the derivative of 1 over 2x? I mean, this is so easy, but like, I mean, I don't have a value in the denominator. I have two values. So do you do like 2x? Oh, bro. Derivative of 1 over 2x. Dude, 2x. What question are we on? What question 11? No, no, no. There you go. All right, yeah. I guess we can see that way. So 1 over 2, x to the power of negative 1. And then, oh yeah, and this a derivative. So we do 1 over 2 times negative x to the power of negative 2, or negative x to the power of negative 2 over 2, right? Wait, how do you? Oh, I see. Okay. Yeah, well, I mean, I think this is correct, but as much a simpler way would be, there you go. Beautiful. Cool. Whatever. So, um, so we have 1 over negative 2x. So, hold on. Where are we? I think. Right. Perfect. So, let's see. Let's see. Wait, is that what we got? Oh, yes. Okay. So now let's see if we can apply L'Hopital's rule. So then we get, uh 1 times, wait, and why do we have a negative 2? Bro, wait, okay, and 1 over x, the derivative is 1 times x to the power of negative 1 equals negative 1 x to the negative. Perfect. So 1, dude, I'm gonna crash out or something. So we have 1 times, so negative x to the power of negative 2. So we have negative or minus, no, sorry, negative infinity, negative 1 over infinity. Yeah, that's what the power of 2 are the same thing. So we or so times, bro. So negative x to the power of negative 2, negative infinity to the power. Wait. Oh my gosh, bro. The derivative of 1 over x. I just don't want to get anything wrong. I'm just checking everything here. To the power of negative 1. Yeah, negative 1 times x squared. We have negative 1 or negative x, and that's the same thing as negative 1 over 2. Wait, what? No. 1 over. Or, okay, let's take out the negative. Negative 1 over x squared. There you go. And dude, please stop. So now, what do we do? Now, so this is also equal to negative 1 over x squared. Right. So 1 times negative 1 over infinity. Yes. Negative 1 over infinity. Negative 1 over infinity. Okay. Negative infinity. This is equal to, so negative 1 over infinity over 1 over, okay, yeah, negative 1 over infinity. Same thing. So this is equal to negative 1 over infinity times infinity. Okay. We get infinity, or yeah, a negative infinity over negative infinity. This is infinity over infinity. Another indeterminate form. Oh my goodness, bro. I'm gonna crash out. Where are we? So, so you do derivative. Oh my gosh, dude. I can't take this anymore. The amount of mistakes I might be getting, but whoops. Bro, wow. How do you do this? Why did I miss it? All right, let's finish this, dude. Yes. For real? Wait, a derivative of 1 over x is negative 1 over x squared? Wait, why? See, a derivative of 1 over x, negative 1x squared. Interesting. Think of 1 over x. Yeah, yeah. I know, thank you. Yeah. Mm, you forgot to close the parentheses, right? Or is it supposed to be e? It's fine. Yeah. Oh, and we can. It's 5e. Okay. Wow, we go like almost 2 hours. Okay. Yeah. Should I restart this problem? Hold on. Where are we? Okay. Here, I'm just gonna do this in my notebook. So we have so mm, yeah, and here we have infinity times 0. Okay, and then we have to play the derivative. So we have perfect. Okay. Um. Oh yeah. Okay. And we do something with that. Um. That a -1. Derivative. Yeah. No, we don't. Yes. Like that. Okay. And then do 1 over negative. Yes. Okay. It's getting a little messy here. How did we get such a different answers here? That's what he did. Oh, okay. So, oh boy, it's already 12. I thought I was gonna end an hour ago. Yet I'm not even close. Come on, we gotta end at least around 1. Um, so we get. So we have all right, and then we play the derivative. Cool. And the derivative of -1 is 0. So I don't do anything there. There you go. Okay. All right. I finally got there. So now we have 2e to the power of 1 over x. So does that work? Oh, we get 2. Let's go. Oh my gosh. We finally did it. Oh, that was tough. My goodness, bro. We have 5 more questions. But no, we got this. So now that we kind of got like through that trial, that mathematical trial, thank you. And by the way, thank you for your help. I really appreciate it. Thank you a lot. Let's see. Now, um, oh wow, dude. So we got 5 problems left. All right, let's do this. So we have the limit as x tends to infinity of x to the power of 5 times e to the power of negative x squared. Now, can we do infinity? Well, let's see. So we get infinity times e to the power of negative infinity. And e to the power of negative infinity is 1 over e. So we got infinity times 0. So an indeterminate product. So now, so So we have a product right here. Now we can express this as a quotient. I think that's right. Bro. Hold on. Let's see. Yeah, no, I think that's good. Okay, so now, does this work? So we have e to the power of negative infinity over 1 over infinity. This is 1 over e to the power of infinity over 1 over infinity, and this is equal to 0 over 0. Another indeterminate form. So now applying the derivative, again, L'Hopital's rule, we get, so we have to do the to the power of negative x squared over 1 over x to the power of 5. So equals, now we have to apply the derivative. And we get, what do we get? We get, wow, negative x squared. That's tough. Okay. So we get e to the power of negative x squared times then the derivative of the function, negative x squared. So we get negative 2x, I think. I think that's what we get. Or do we have to apply the chain rule again? Oh, come on. We forgot to apply the derivative here. E to the power of negative x squared. And you just do the derivative of the inner function. All right. And then the derivative of 1 over x to the power of 5, and that is equal to 1 times x to the power of negative 5, a derivative of that. And that equals to negative 5x to the power of negative 6. All right, cool. Beautiful. Let's go. So now that equals to, so e to the power of negative infinity times negative infinity over negative, whoops, and this equal to 1 over, so we have 1 over negative 5x to the power of 6, and that's equal to 1 over negative infinity. That equals to, we in e to the power of negative infinity. E to the power of negative infinity. I have no natural logarithm here. What is e to the power of negative infinity? Oh, wait, hold on. So we have 1 over e to the power of infinity, and that's 0, right? 0. So we have 0 times negative, well, I'm getting nowhere. And 1 over, 1, what? And 1 over negative infinity. Gosh, I'm not getting anywhere, dude. So we apply L'Hopital's rule again. Well, no. Gosh, okay. So L'Hopital's rule, okay. We get, ooh, wait, how did, oh, dude, I really hope I'm not getting any mistakes right here. So that was the second application of L'Hopital's rule, and we get negative 2x. Okay, so now here, this is the third. Times negative 2x. Is that what's going to have to happen then? So e to the power of negative x squared times e to the power of 2x times negative 2x times negative 2x. So the derivative of the inner function times the derivative of the past inner function. Oh my gosh, dude. I mean, I really hope so. Negative 5x to the power of negative 6. The derivative of that is 30x to the power of negative 7. Wow. And now applying that, we get 0 times. Dude, we're not getting anywhere. What in the world? We're just going to go in loops and loops. Negative infinity times negative infinity. Yeah, bro. 1 over infinity. Dude, what do you want me to do? I mean, I'll just Copilot do this. There's absolutely no way to solve this, dude. Oh my goodness. Hmm. Dude, these problems are getting hard. They're requiring more problem solving. So applying L'Hopital's rule, we get x to the power of 5 over e to the power of x squared. Yeah, that makes sense. Now, does that work? We get infinity over. Stop giving me an indeterminate form, bro. So we have e to the power of x squared, e to the power of infinity. That's simply infinity over infinity. Well, that's why we weren't getting anywhere. You could repeat, but it's overkill. Yes, will keep reproducing itself. That's the thing. Yes, so what does that mean? So, wait, what does that mean? So is it 0? It is 0. Wait, but hold on. Wait, so I was doing it right? After 5 rounds, The numerator. I see, okay. So I was doing it correctly, but like in a very messy way, I think. Yeah. Yes, I agree. Okay. Ooh, we got 4 problems left. Oh boy. Let's do this. So, this equals to infinity over infinity. We get an indeterminate form. So what we do is apply L'Hopital's rule. Oh wait, well, kind of get 0 for this one as well, right? Since we have x to the power 15. Right? Okay. So looks like it doesn't work. So let's continue. Oh boy. Oh boy. Okay, so no, this is incredibly easy. I'm sorry. Why are we whining? No way. This is incredibly easy, dude. No. You're right. Incredibly easy. So here we get infinity over infinity. All right, finally. Again, applying L'Hopital's rule again. We get 2 over 15 times 14. 15 times 10, 150. 15 times 4, 60. Wait, for real? Yeah, 60. 150, 210. We get 210 x to the power of 13. This equals to 2 over infinity. Or in other words, we get 0. The heck? We get 0. Fine. Then should we? Oh, and that's 0. Yeah, dude, I swear, that's 0. What are you talking about? Why is that wrong? 2 over infinity. What are you talking about, bro? Oh, I'm sorry. We have as x tends to 1, not 0. What are we doing? So we get 2 over 210. Or we get 1 over 105. Whoops. That's also wrong. Hold on. First of all, okay. No, 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 no. Stop, stop, stop. We did this all wrong then. So here we get 1 minus 1 over over 1 minus 1. That's 0 over 0. So we can't do that. Then here we get 2 over 15. Oh, so let's do 15s then. Whatever. We have 3 problems left. Oh. Mm, yes, that's right. Yeah. That's what happened last problem. Yes. Oh boy. Okay. We have 3 problems left. What are we gonna do? What are we gonna do, guys? We will continue. How long is this? That's 8 minutes. All right. So it looks like. Mm-hmm. Mm-hmm. X. That's gonna be just infinity. 1 raised to infinity. Yes. Yes. Okay. I see. As x tends to. Okay. Okay. Oh, no, you can't. I see. X over 5. What? Okay. Yeah, why? Oh. Oh, no, no, I see. I see. Okay. Yes. Yeah, that's why we couldn't do it in the first place. Yes, uh-huh. Um, 1 plus 2 over x. So e to the power of what equals 1 plus 2 over x? Why did that equal 0? Oh, wait, but you can do that. You still gotta solve for the natural logarithm, though. E to the power of what is? Yeah. Okay. I see. Okay. What you focus on the derivative though? Okay. Yes. Uh-huh. You get 1 over 1 plus 2 over x times negative 2x to the power of negative 2. Wait, what? Mhm. Would Mhm. Eat where? Where? What did he do now? Okay. Bro, wow. My goodness. This algebra is getting a little complicated. Okay. Okay, thank you for your help. Thank you. Do you oh, okay. Bro, wow. Here we go. Now comes the hard part. Ooh, this is tough. This is pretty tough. One plus 2 over x. Oh my gosh. Wait, mhm. Okay. Come on, bro. Oh, yes. Okay. What is it? Oh. Wait, why x squared? Oh, wait, no, no, no. You're right. You're right. Yes. Mm-hmm. All right. So I think what he's doing here is Confused. How did he do that? 2/5. I mean, if you did x squared, so you should have, but why 1/x²? I'm confused. 237 minutes. Incredible. Oh, 2/5. 2/5. Oh, I see. So since we had like a negative, oh, so if we do this, if we do 8, I know I kind of like my way of doing it. Yeah, I'll just, in fact, yeah. Yeah, -8 over, in fact, I'll just have 8/10. Mm, so that's equals to 8/10. And this final equals to 0. So it's just 8/10 or crap. Okay. But how did he? It would be cool if he could explain. Okay. A minus divided by a minus. Where do we get that? How did he do that? A minus divided by a minus. So I'm guessing he did -2/x² times x² over -5. Well, sure. Okay. The way he did it's very weird, but again, so we get 8/10, and then I'm guessing. So since we left the negative on the denominator, um, hold on. Oh my gosh. How did we get that? Oh, wait, no, 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 no. So this is the denominator of the first fraction. This is over. Oh, 1/. Oh, I get it. I get it. Kind of. I think I kind of get it. So we have 8/10. Yeah, well, precisely what I got. Uh huh. Wait, but what's wrong with what we did? First 0. Mm-hmm. Right. 1. 2/5. Okay. So what did I get? Yeah, 8/10. Oh, sorry. E to the power of that. E. So we were right. We were right. We just forgot to. There we go. Oh my gosh, bro. 2 questions left. Oh boy. We have 2 questions, guys. This is incredible. Don't know what to do. No. Well, we got to finish this. Come on. Let's. Oh, and we got a video. Do we have a video? Okay, I know video there. Mm, all right. Mm-hmm. That's gonna equal, I think, 0. So 0, 0. Yes. Right. Uh-huh. So yeah, you apply the natural logarithm to both sides, and then you can take out the 3 sine of x. Oh yeah. So yeah, you put it inside, uh-huh. You take out the wait, and what did you do here? You took out the 3 sine of x, you substitute natural logarithm of x. See? Oh, wait, hold on. Yeah, yeah, you can do that. So let's see. So you've simply simplified. You've not applied L'Hopital rule 2 times. So if that's the case, gosh, what was that? Whatever. So 3 sine, so that's 0, and then the natural logarithm of x, which tends to 0. So 0, negative infinity. So we have another indeterminate form. Okay. Okay. Then what? Oh, you put it in a quotient, right? That's what we need to do. 3 times natural logarithm of x, and then you put 1 over sine of x. Okay. And then, oh, and that's equal to cosecant of x. Okay. Hopefully we don't have to do the derivative again, but we probably will. 3 cosecant of x. Okay. And what does that equal to? That is going to be negative infinity over. Wait, 3 over x. Oh, that's right. Cotangent of x. Yeah, so he applied the derivative again. Wait, for real? That's what he did. Um. Okay. Oh boy. Now we had to do all of that. This is gonna get tricky. All right. So let's do up till what we know how to do. So we have the limit as x tends to 0 from the right of x to the power of 4 sine of x. So we do this by first. So we notice this is going to equal to 0 to the power of 0. Perfect. So now we apply the derivative to both sides. Do we have to do that first? No. Sorry, we're not going to do that. We're simply going to apply the a natural logarithm. You get 4 sine of x. Yeah, we'll just simplify easy right there. Times a natural logarithm of x. Right. Uh-huh. Hold on. So what happens now? Or more like, it did, what step do we miss? Natural logarithm of x. Oh boy, oh boy, oh boy. Wait, what? No, 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 no. My bad. Sorry. Yeah, so here all we're doing is simply simplifying. All we're doing here is simply simplifying. Come on, bro. Get out of there. Stop. Cool. So you apply the natural logarithm. Sorry, so we have 4 sine of x times natural logarithm of the base, because that's what we want. So we only have x right there. And then, oh yeah, parentheses there, and then to 0. So we have 0 times negative infinity, okay? So now we apply the derivative. We get x, oh boy, this is gonna get ugly. Oh wait, no, 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 I'm sorry. Oh, we didn't do that. We're already past that. What we do is, oh, in fact, no, I'll put this in a quotient then. Dude, I'm getting tired. I'm getting actually tired. Um, what do we do? So, let's see. So we have a 4 times uh e to the power of what? A negative infinity. So we have a negative infinity over over 1 over 0. So that is infinity. We what? Whatever. So then we do the derivative of that, 4 over x over cosecant of x times cotangent of x. Dude, wow, I'm getting hungry. I need to eat. Uh oh, so one. Let's say you put it in the x. Wait, why do you put it in the 4? Oh, I see. Oh yes. Oh yeah, because we also have sine. So we can express. Wait, and what do we have? A negative a cosecant. Wait, why is that? Bro, wait, hold on. Why? Why do we have a negative? Oh, dude, I swear if that's by accident. Why? Oh, negative. Just okay. By definition. Okay. I see. All right. So here, this is negative. By definition. So here we then get negative 4 times. So we have 1 over a sine. So then I'm going to sine of x, and then we have we have cotangent of x. So that is 1 over tangent of x. So then we're gonna have a tangent of x. Okay. All of that over x. Okay. I believe that's what he has, right? Then he applies, wait, what does he do? Oh, okay. So then he does that weird trick. I don't know why, but it seems like it works. Okay. Oh, so we can get sine of x over x. So we saw that the limit of that as x tends to 0 is going to be 1. So we and for tangent of x, tangent of x, sine of 0, sine of 0 is 0. 0, 1, 1, 0, 0, 0, 0, 0, 0. Okay, so we get 0, huh? 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Oh, that's going to be 0. 0. Yes. E to the power of 0. E to the power of 0. Uh-huh. E to the power of 0. Yes, that's what we get. So then we get e to the power of 0, and that's going to be like 1, right? We have one freaking question left. Come on, guys. Is this live or streamed? No, this is literally live. This is live. No worries. No worries. This is live. But we have one question left. We have literally one question left. Wow, we almost go 3 hours into this live stream. Well, welcome. Welcome. Hi. Hey, it's good to have you here. Well, we've one question left. Oh my gosh, dude. Oh boy. Okay. Oh, here we go. Here we go. We've one question left. One question left. Okay. So we have the limit as x tends to positive infinity of x to the power of 8 over x. Okay. So this is going to equal to infinity to the power of 0. So that's an indeterminate function. So applying the derivative, we get x to the power of 8 over x times, so what is the derivative of 8 over x prime? This is 8 times x 1 prime. This is going to equal negative 16x to the power of 2. Whoops, that's not right. This is simply negative 8. Negative 8. Beautiful. Okay. We're going to do the natural logarithm of that. Okay. What else? What else? So now can you do that? Can you do that? Infinity. So we have, but because we have an exponential function, then we gotta. I'm guessing we gotta find a trick. And what's our trick? Okay, hold on. So we have, yeah, no, dude. Oh, and this is. Oh wait, hold on. I think we got this. So a natural logarithm. Okay. So then we do x over x. Okay. There you go. So I'm guessing this tends to infinity. E to the power of infinity. I think. Okay, that's wrong. Inf is not defined. Oh, sorry. Not E. That's not right. No, E. Actually, yes, E. Now, so the natural. Yeah, so yeah, here we're simply going to get infinity to the power of 0 over negative infinity. Yeah, we're not going to get anywhere. So I believe. Hold on. Let me ask if this is the same case where we simply have to observe the powers. chat. Right. Uh-huh. Wait, isn't that wrong? Why? Natural logarithm of that. Oh boy. Wow. My goodness. Rewrite using exponentials? What are you talking about, bro? Oh, wait, hold on. No, no, no. That's what we're doing, though. Uh huh. Yeah. Uh huh. Yes. Oh, crap. We forgot to do that, though. Mm hmm. 8 over x, natural logarithm. Oh, hold on. No, no, no. We simply want to rewrite this expression. Mm hmm. Yes. Here, in fact, okay, let's do it the way he's doing it. I like it. So we have. Oops, wait, no. Uh huh. Yes. Okay. Um, why do we need that? Oh, so do we do like a derivative or? Oh, no, 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 no. He he's simply simplifying. Mm, so he does eight. Oh, okay, yeah. Uh huh. So one. Okay. That was crazy. That was crazy. My goodness. That's enough math for today. That is enough. That's enough for me. Well, thank you everyone for watching. It was a lot of fun and it was tough. So I will see you all next time. Thank you for joining this live stream.